All right, let's dive into a concept that's, well, absolutely fundamental to how engineers think about energy in the real world. It's called enthalpy. And honestly, it's one of the most brilliant shortcuts that makes everything from jet engines to power plants even possible. So let's get right into it. You probably remember this from school, right? It's the first law of thermodynamics, the golden rule of physics. The total amount of energy in the universe is fixed. You can change it, you can move it around, but you can't create it out of thin air, and you can't just get rid of it. Sounds simple enough. Well, that simple rule gets a whole lot trickier when you're not just looking at a static object. What about systems where stuff is constantly flowing in and out? I mean, how on earth do you balance the energy checkbook then? To get our heads around that, let's start with the easy version. Imagine you've got all your energy neatly contained inside a sealed box. In engineering, this is what we call a closed system. So what's the big difference? It's pretty straightforward. In a closed system, the amount of stuff, the mass, is locked in. Nothing gets in, nothing gets out. But an open system, that's how most things in the real world actually work. Mass is always on the move, flowing across the system's edge. So it's time to open that box, because as soon as we do, we start to see how engineers have to think about energy for pretty much every piece of technology you can imagine. An open process is exactly what it sounds like. It's a system with an open door policy. You've got mass coming in one side, something happens to it in the middle, and then it flows back out the other side. Think about a car engine, a pump, heck, even your own body. Okay, this here is basically the blueprint for any open system. Now, don't worry about the math and the specific letters on the screen, just focus on the flow. You've got an inlet where stuff comes in, a process unit where the magic happens, and an outlet where it leaves. That simple idea, in, process, out, that's the key to this whole thing. So here's the catch. When you have mass moving across a boundary like that, it turns out there's a kind of hidden energy cost. It's not free to just move stuff around. And this cost has a very specific name, flow work. Just think about it for a second. If you've got a pipe or a tank that's already full of some fluid and you want to push more fluid in, well, you got to shove your way in, right? It's like there's an energy toll you have to pay just to get through the door. If we look at the inlet, the stuff outside has to physically push to get new material inside. It's doing work on the system. The best analogy is trying to push your way into an already packed room. That effort you expend, that's an energy input. And, you guessed it, the same thing happens on the way out, just in reverse. The system itself has to use some of its own energy to push the processed material out into the world. So that's energy leaving the system. So you've got work being done on the system to get in, and work being done by the system to get out. For an engineer trying to figure out if a process is efficient, what really matters is the net result, the difference between those two. And that difference, that's flow work. It's the net energy that's purely dedicated to the job of moving mass through an open system. It's a piece of the energy puzzle you would completely miss if you were only thinking about those simple sealed boxes. Okay, so now we have two things to track. The energy a substance already has, that's its internal energy, and now this brand new thing, flow work. Keeping tabs on both of those separately, it gets messy. So engineers came up with a really clever solution. I mean, just imagine for every single calculation, you have to figure out the internal energy of whatever's flowing, and then you have to calculate the work needed to get it in, and then the work it does on the way out. It's a total headache. And this is where enthalpy saves the day. Now, enthalpy isn't some magical force of nature. It's a property that engineers literally invented to make their lives easier. You can think of it like a thermodynamic combo pack. Enthalpy, which we represent with the letter H, is simply the internal energy of the stuff plus its flow work, all in one. And this shortcut is just so powerful. Instead of juggling two separate complicated terms, engineers can now just calculate one single value, the change in enthalpy from the inlet to the outlet. It wraps the whole problem up into one clean, elegant package. Now here's a really interesting detail from the source material. You can't actually know the total enthalpy of a substance. It's impossible. There's no absolute 0.4 total energy. But, and this is the key, it doesn't matter. Because all an engineer ever needs to know is how much the enthalpy changed as the substance went through the process. So, to measure that change, everyone agrees on a standard starting point, a reference state. The best way to think about it is like measuring the height of a mountain. You don't measure it from the center of the earth, right? No, you measure it from sea level.
Sea level is just an agreed upon starting line so that everyone's measurements make sense together. Same idea here. So why have we gone through all of this? Why does enthalpy matter? Because this one single concept is woven into the design of pretty much the entire modern world.
So the next time you see a massive chemical plant or a power station, just remember this simple diagram. The only reason those complex systems work safely and efficiently is because engineers can precisely balance the energy budget, and they do that by using enthalpy.
And this is not just theory. This is absolutely critical for designing power plant turbines, jet engines, chemical reactors. Even the air conditioner in your house or the refrigerator in your kitchen works because of these principles. It is everywhere.
So the bottom line is this. Enthalpy isn't just some random word in a science textbook. It is a powerful, practical, and really elegant shortcut that is fundamentally built into the design of the machines that run our world. It really makes you wonder, doesn't it? What other brilliant ideas, these amazing shortcuts like enthalpy, are hiding in plain sight, just quietly making everything we do possible. Thanks for tuning in.